What is up, most distinguished viewers of this channel? Today I have a treat for you guys, and it's something a little bit unconventional, but we're going to learn a ton about high strength welds. So that's what we're going to talk about today. Let's get into it. So today's video is in response to a ton of questions and comments I've gotten over the past year or more dealing with higher strength rods or fillers. And it's pretty common because when you get into welding and you realize there's all these numbers on your rods and your MIG wire, your TIG wire, and well, if 70,000 PSI tensile strength is good for your wire or your rod, why not go to 80 or 90 or 100? And what are the detriments to that? And I thought it was worthy enough to answer this question to do a whole video on it to where we can all learn a little bit more about higher strength fillers. So what I have in front of us here are some common, so these two welding rods, and then we have some less common ones here. We have something that's a high strength filler for a particular purpose that you would not want to weld with, and then we have some stuff that you probably maybe know exists, have never ran, or never seen. So let's start out simply by looking at this package right here. We have standard 7018. This is a particular rod I prefer to run, ESOB 7018 Prime. Love the rod, great rod. Anyways, this for stick welding is an excellent rod. It will perform great on normal mild steel, and it also to a certain extent can weld higher strength steels. Caveat to that is that for the particular purpose, it's not detrimental to have a weaker weld. And that's pretty common on certain materials like chromoly, for example, to under-weld it. And what I mean by that is to weld it with a filler that is actually weaker than the base material. The common reason for that is because the base material itself will often fail in a heat affected zone before the brittleness or whatever the strength of the weld becomes an issue. But again, when you start dealing with materials like that, you really need to know what you're doing and follow proper procedures for that. But anyways, back to what I was saying, 7018 for stick or ER70 MIG wire, TIG wire can take care of most of the jobs that you might have to tackle in your home or your shop. However, there are severe limitations of this rod, one of which is it's not ideal to weld higher carbon cast iron because it produces a very brittle weld, so not ideal for that. And it is not ideal for joining certain higher strength steels because after a certain point, the weld itself, if it's welded with 7018, becomes the weakest link. And that high strength steel, you're losing a lot of strength in what you're welding by using it. And that's where different fillers come into play. Now, I'm going to move this out of the way and we're going to talk about this guy right here. This particular rod I have actually never run, and I'm going to be pretty interested to see how it runs because I have heard it runs just like a 7018, or at least somewhat close to it. But this rod is not something you would generally want to use to weld mild steel, and there's a lot of reasons for that. I'll get into that in a few minutes here. But 11018, we're going to do some welds with that. And we're also going to do some welds with this particular product here, which thank you to whoever sent me this. I apologize that it took me this long to get to testing this. I had been waiting for a good time, and well, now's a good time. But thank you if you're watching this. I appreciate it. And we're going to try this out. What this is a 80,000 PSI tensile strength rod. So it is not exactly a 7018, and this is not a classified rod, meaning the American Welding Society does not have a standard for this. This is outside of the scope of your typical 6013, your ER70 MIG, all of that. This is a proprietary blend of secret herbs and spices to give a stronger weld that's supposedly a very easy to run rod. I have never ran it, and I will find out today if that's the case. But this arguably will deposit a weld that is stronger than 7018. So we're going to look at welding a fillet weld with that and bend testing it and see what happens. Over here we have hard facing. Hard facing is a great example of something that has typically anyways very high tensile strength, but it's not suitable for welding. And by welding, I mean joining two pieces of metal. This is meant to lay like a bead of caulk on something and resist wear. What makes it great for that purpose probably is going to make it extremely terrible for the purpose of joining metals together. And I anticipate when we bend test this that it will likely fail, just like I think 11018 may fail. I'm not positive, but it's possible it will if we can get it to where it welds, and more on that later. Now we have, for the final one, is a problem solver rod. Again, a AWS unclassified rod that is designed for the purpose of solving problems. And if you look at the picture on here, they're showing things like leaf springs and coil springs and anvils and hitches. I don't know why on earth you'd be welding a hitch on your car, the ball anyways, but it is what it is on that. But this essentially is just 312 stainless. I can tell because of the flux coating and how this product runs. It's just 312 stainless, which 312 stainless can weld a lot of things, including high carbon steel, and not become brittle, because the brittleness comes from the carbon absorption. This, being chromium, nickel, etc., does not become brittle with carbon absorption. So this can be a problem solver for welding dissimilar metals or tool steels or stuff, but it's not necessarily the most ideal rod to be using in all circumstances. And when we bend test a weld with this, it'll be interesting to see what happens. So that's just a brief overview of what we got. Let me do some quick book learning with you guys so we're all on the same page, and then I'm going to weld up a bunch of stuff and we're going to bend it and see what the hell happens. All right, guys. Today's book learning session is going to be probably one of the most important ones I've done, so please pay attention. This will help you understand a lot more about welding high-strength steel, and it's very important because if you do things wrong, you could suffer severe catastrophic failures. And I'm not trying to be doom and gloom here, I'm being honest with you guys. So grab yourself a beer or a popsicle because it's hotter than shit outside, and let's go through this. So to start off, let's talk about 7018. 7018 is a known test result. It's a classified by American Welding Society rod. Same thing with ER70 MIG and TIG wire. They are known entities. They have very reliable performance, and they've been used on all sorts of materials. So the result of welding on those materials with that product are well known and documented. So it makes it very easy to determine if that will work for your needs or not. On the contrary, when we look at AWS no-spec or non-spec rods, like these problem solvers and the Blue 80,000 rods, we don't have known testing. Now, in all fairness, there may be test results available from the manufacturers, but now you got to be a metallurgist to determine if that's somehow better for what you're welding than, say, 7018. And that's a variable you probably don't want if you're welding anything with liability or that needs strength. Now, there is a caveat to this, and that is, like this problem solver rod is designed to weld high carbon steel and not suffer extreme brittleness. Like, say you wanted to weld on an anvil and you use 7018, that weld could be so hard and brittle it just cracks right off of it. Welding it with this problem solver, which is nothing more than 312 stainless, may give you a lasting weld that's not brittle, because 312 stainless does not become brittle with carbon absorption. So there are certain uses for non-classified rods that could benefit you, okay? But they're few and far between. So let's talk more about the 11018. 11018, 8018, all those rods are AWS specs, so they are known test results. And the materials that you would use them on are also very well documented and known to where you can get reliable results. Where you kind of throw a monkey wrench into the mix is using a rod like this on something that either doesn't need it, so like mild steel, or on an unknown steel. You can suffer catastrophic problems such as extreme brittleness or failed welds, and we don't want that. And I'm going to sum up kind of what's going on with the higher strength rods as simple as I can, and that's this. High strength rods are just like high strength materials. High strength materials have certain criteria that must be met in order for them to be weldable, or for welds to, quote, stick to them. If you don't follow those, you're going to suffer failures. So it makes sense if you think about it that higher strength rods would have all of the same issues that the material they were designed to weld do. And that's why you can run into serious issues trying to substitute, say, 110/18 for a 70/18. It's not just the tensile strength increase that you're getting with it. You're also getting a lot of things like these. So let's go through that list quickly. High strength steel often requires a preheat to a minimum temperature. That could be because the material's hot, short, sensitive. It could be because if the weld cools fast enough that it shrinks and cracks. So it could be for the base material, it could be for the rod, it could be for any number of things. So a preheat is not required typically with 70/18 to weld mild steel. Now, if it's -60 out, you probably would want to do that. But for just room temperature steel, no preheat is required with 70/18 on mild steel. 110/18, if you were to weld that on high strength steel, you would need a preheat. However, one of the issues here is that if you were to weld mild steel at 110/18 and you didn't preheat the mild steel, it's possible that the weld may cool too fast and then crack. And we may see that today when I weld mild steel with this product, is that the weld may not even make it to cool down before it fails. I don't know for sure, but we're going to find out on that. So that is a detriment. So preheat is a concern. Now, non-AWS spec, who the hell knows? It might not. Again, we have variables that we don't know about. So that's not good. Now, post heat, which is basically keeping what you welded warm for longer and slowly cooling it. Post heat can be required with higher strength steel as well as when you're welding with 110/18. 70/18, generally speaking, for anything you might do, not really required. However, if you saw my previous video where I water quenched a 70/18 weld, that made it extremely brittle and it failed during a bend test. So cooling it rapidly isn't good, but just letting it air cool, is, however fast it does, isn't a detriment for that. It is for this. Now, again, non-AWS spec, who the hell knows? Now, inner pass temperature limits. This is something a lot of you have probably never heard, but it is super critical with higher strength alloys. What this is a maximal temperature that the material can reach between passes. So you run a pass and it's hot, you have to let it drop within a window or keep it within that window before you go and weld on it. And if you do 3 passes super fast, your weld's probably going to fail, or the high strength material is going to lose the properties of it being high strength. So 70/18 and mild steel do not have inner pass temperature limits within reason. Again, you don't want to do 10 passes as fast as possible because your weld grain structure will be poor, but it's not as strict or anywhere near what 110/18 or many higher strength alloys. And again, not to sound like a broken record, we have unknown on the non-spec. Impact resistant. Now, this is one of those things where certain hard face rods have very high impact resistance. However, that comes at an expense of other things. So impact resistance is a big unknown with non-classified rods. And with these, guess what? You weld mild steel with 110/18 and you may get a change in impact resistance that is highly undesirable for what you're welding, versus 70/18 might be better. So just because something is higher in strength does not necessarily mean better. A couple other things I want to cover real quick too, and we'll get to the welding. What I'm trying to get at is, if you're welding on known steel, you're best off using known classified rods that are designed to weld that steel. If you're welding on unknown steel, which is very common, I mean, I don't know for sure 90% of what I welded in my life what it is, but you can take certain guesstimates on it. Like, is a dump truck box going to be made out of high strength steel? Probably not. Is something from NASA going to be welded with high strength steel? Possibly. So simply by looking at what you're welding gives you a good idea as to whether or not it is a higher strength alloy and then would need a higher strength filler. For certain parts that are in the ground, like get pulled behind a tractor, would those be higher strength steel? Absolutely. Would 70/18 weld them? Possibly. Is that the right product to use? Possibly not. You don't know. And that's where there's certain tests you can do as a shade tree welder, per se, that can give you a better idea on what you're dealing with. And that's a whole video in itself that I'll have to come out with soon. But for the sake of what we're talking about today, for most of what you're going to weld, rarely would 11018 give you a benefit, or non-spec rods. You're better off sticking with known entities like 7018 and ER70. And to answer the question, and well, we're going to do weld tests to find this out, is there such a thing as too strong of a weld? Absolutely there is. If you were to weld mild steel with 11018, there's a high probability of weld failure before we even go and bend test it, because it has properties, just like I said earlier, of the base material it's designed to weld. And therefore, if you don't follow all of these things, just like we went through, you're going to suffer weld failure. Not to mention, hydrogen embrittlement of 11018 welds is a very serious concern. So these rods must be kept in a rod oven, and the material must be typically preheated in order so that moisture doesn't form on the surface of it, especially if it's at room temperature, because hydrogen in this alloy and the base material it's designed to weld would be a serious detriment, versus mild steel in 7018, generally not the biggest concern in the world. So I think you have a better idea of this. So let's get into actually doing some welding. So I did this plate weld and a bunch of fillet welds. I thought before I cut and etched this, just to look at the penetration, that I would point out some interesting things. So this first weld here was the 80,000 tensile strength Messer MG80, and it welded like a combination of a 6013 and a 7024. I've never ran a rod ever that ran like that. It slag peeled like 7018, smelled like 6010, and yeah, that's its whole different entity, I guess. Now, I ran that at about 110 amps. I did not have any chart to go by, and I tried looking it up. Had no amperage range. It appears to have made a really small, narrow bead. Maybe if I increased the amperage, it would have helped it a little bit. But odd running rod, it ran okay, pretty easy to run. So I guess all of that are good things. We'll see how well it does in the bend test. Now, the problem solver rod, just as I said, 312 stainless. You can tell it's a stainless alloy because if you look at all of these, which one is the rainbow colored? This guy. And stainless produces very vibrant colors and pure silver when it's shielded properly. So this clearly is a form of stainless steel filler. That welded very much like what I would have expected out of 312 or 308, 309 stainless. Nothing really to speak of there. This guy right here is the hard face. It welds very similar to like a 7024. Has a lot of real fine spatter, kind of like a 6010 maybe, but very easy rod to run. No real complaints there. The weld is definitely hard. This guy right here is just a traditional 7018, nothing really fancy. And then this was the 11018. The 11018 was a lot harder for me to start. I was running at 120 amps. I would have liked to have started at a higher amount, as well as I should have enabled hot start. This rod seemed to be a little bit more difficult, like I said, to start. It ran very similar. It looks just like 7018. Maybe the color's slightly different, but very similar. Now, the interesting thing was when this thing was cooling, I heard a whole lot of pings and pops like welds were cracking. I don't see any evidence of it on any of these, but that's generally not a good sign on mild steel to hear that. All right, got the cut and etch done. Let's take a look at it. So we'll start on the left. The 11018 looks just like a 7018 bead. So mild penetration, not really anything to write home about, pretty smooth bead profile. The 7018 next to it is a little bit rough. That's just that section of the cut and etch, but most of the time it's going to look more or less like the 11018. Now the hard face bead has elements that you don't want to see. So deep penetration, that's not something you want in a flat bead profile. The amperage that I was running it at was probably a bit too high, and that you don't want because the bead will tend to dilute too much into the base material and crack. And speaking of cracking, more on that in the next section. Now the one next to that, the 312 stainless, you can tell it's stainless by looking at the bead. It has that shiny chrome appearance. And 312 stainless is a very low penetration rod, and increasing the amperage generally doesn't cause it to wet out anymore, and that's what you're going to expect from that. Does not appear to be cracked or anything, which is good. And then the MG80 at the end, very mild penetration, to me looks a lot like a 6013 rod, so that's quite an enigma of a rod, to be honest. Now speaking of cracks, let's look at that hard face bead up close. So I looked at this up close in person and in this picture as well, and I'm 99% certain that on at least the left side of that bead, that's a crack there. I sat and polished this multiple times, and there always seemed to be like a raised, distinguishable line there. It didn't like blend in, and I'm pretty sure it cracked, and that would go along with the pinging I heard as one of the welds was cooling, or at least this one, I believe, is what was causing the pinging as it was splitting off the base material. Now, I don't think this is hydrogen embrittlement cracking. What we have here is what happens when you run an alloy too hot into a base material and the alloy is really hard, abrasion resistant. Well, what ended up happening is it mixed too much with that base steel, and when it cooled, it just basically couldn't handle it and cracked off. Had I dropped the amperage to more or less get that bead to lay on the plate like caulk, it would have never cracked off, and you also get better wear resistance. Remember, because this is diluted with base material now, it's not as hard as it would have been if it was a bead of caulk. Oh well, let's move on. So that was pretty interesting. And I gotta say, I'm kind of surprised the 11018 didn't crack. I'm not surprised at all that the hard face did. Ran a little bit hot and had a little bit too much dilution of that material into that plate. And that is to be expected. And that's one of the reasons why you don't use hard face to actually weld something together, which is gonna be pretty interesting when we actually bend test something that I welded with hard face. So speaking of that, let's go and bend test. All right, guys, I thought I would do a quick inspection before we go and bend these and just give a couple opinions on this. So I ended up doing 2 of the 80,000 blue rods. I found that I ran it at 110 amps and I had undercut on the first one, and I thought it'd be kind of unfair to test it. We're still going to break it, but I went back and reduced it to 95 amps and had a lot better luck. There's really no undercut. There's still some slag on the toes, but hey, it is what it is. Now, that rod runs, I don't know, like the amperage of a 6010, but it runs like a combination of 6013 and maybe 7024. It seems to produce a decent looking bead, so that's a plus, but a very small bead, very low deposition. Interesting rod, so hopefully it passed bend test. Now this 312 stainless produces a very wide flat weld, and I was cramming a rod in there and it's still like it was difficult to control the arc, and that's typical with the 312 stainless. I use it mainly as a repair rod, and the quality of the first pass of the weld is kind of little concern, I guess, because I normally use it on things like cast iron and spring steel, etc. So you're welding on stuff that doesn't weld good anyways. Now there is some hard spatter on there, some buckshot. Maybe the arc got a little bit too long, but I don't know. It is what it is. Interestingly enough, and it probably will affect the strength of a bend test, there's a lack of fusion between the start of the plates. I'll take a picture up close and post it now, but I've never really seen that with most rods. Maybe if I would have sat there for a little bit longer before I moved, I could have taken care of that. Or I could have done a start tab and started on that instead. In the field, I would have just ground that out and then welded over it. So it's not really like a big issue from a repair perspective. It may affect the strength of this test, but we're still going to test it anyways. Now the 110-18 runs, I would say, a little bit different than 70-18. It produces a bead that looks almost identical to 70-18, which you would kind of expect, that being that the flux is somewhat similar. No undercut, pretty small bead, nothing really to write home about. Shockingly enough, it did weld on here, which is a room temperature plate, and did not fracture or break that I heard. I didn't hear any pinging, so that's really good. That's a great sign, and I don't know, at this point I think it might actually bend test out. Now this hard face weld, that's a little bit different of a story. So you would never want to use hard face to make a weld, but I did. I heard some pinging from this, and there's a lot of suspect points like over in here on the toe line that may actually be cracks. I would have to bust out my little microscope to really see up close if that was the case, but I don't anticipate this passing a bend test for a couple reasons. One, I think it's just going to break, and two, it produced a really weird concave bead, so the throat depth of this weld is pretty poor, so that alone I think it's going to end up failing a bend test. But it's a prime example why you probably shouldn't use hard face to weld crap together. All right, let's go over to the press and bend all this crap. So up first is the blue 80,000 unclassified rod. This is the one with some undercut and weld defects. Let's see what happens. Catastrophic failure. Not too surprising. Be interesting to see if it was caused by the undercut or not. I don't think it was, but we'll find out. This guy right here has no undercut, and by all accounts is a good weld. Let's see if this one also fails. And catastrophic failure. Not too surprising. Now let's try the 312 stainless. failure as well. That was far stronger than the 80 series rods as far as how much stress actually hit the weld. Let's do 110/18. Break there, top toe, interesting. All right, and last but not least, the hard face rod, which this guy, I have a feeling is going to be the worst catastrophic failure out of all of them. Wow, I didn't even put any pressure on it and it broke. Jesus. All right, well, that was exciting in some respects and not really in others. All right, let's go to the bench. So let's start by looking at the 80 series rods, the blue one in particular. So this was the first one that I bent and it broke. Looking at it, it looks like it probably tore at the undercut and then spread down the rest of the weld. So defects on the weld caused the strength loss. The second one that we did that was defect free. That one broke as I would have expected for this particular rod, which is kind of more or less right down the middle. Not all rods will break like that, but this one in particular did. Based on what I see here, well, one thing, penetration is very limited with this blue 80 series rod. The weld itself appears to be fairly strong as far as the pressure it took initially, but once it was pulled, stretched at all, it kind of broke. So I would say this rod, the welded deposits is pretty brittle. Now the question is, okay, this is an 80,000 PSI tensile strength. Is it better than 7018? No. And one of the funny things that you might be shocked to find is that 70,000 is the minimum testing strength. The actual results of most 7018 rods put it well over 70,000 PSI tensile strength. So this rod, in reality, could be weaker than 7018. Now, there is a couple benefits to this rod, which the main one being it runs on all polarities. It runs pretty decent. It's easy to start, easy to restart rod. So if you have like a buzz box, it might give you an option that'll run a little bit better than a lot of the 7018s out there. But is it a replacement for 7018? I would say definitely not. Now, they market it as a kind of dual rod where it can weld maybe dissimilar metals. I don't know how well that would work. I'm not really going to test that. But for me, I'm not going to use this as a replacement for 7018 any day of the week. It doesn't perform as good in my opinion. So let's look at the 312 stainless. So the 312 stainless is quite an interesting rod. Now, it took a fair amount of stretch and strength before it failed. It did ultimately fail exactly like I suspected, and that's likely the starting point for it where it had that lack of fusion. Now, could I have ground that out and welded it and did a better job on that, fixed the mistake, or just ran another one? I sure could have, but honestly, this still would have broken. I've done a lot of testing on 309 rods off camera for jobs and projects that I had to do. and this is going to perform similar, and it's not likely to fully bend before something fails. And a lot of that, believe it or not, isn't because of the strength of the material of the weld. It's actually pretty high in tensile strength. The issue is 312 stainless generally deposits very thin welds, and it has very poor penetration. When you combine those two things and do a single pass weld, there simply isn't a whole lot of weld material to hold this. And you can see how wide and flat that spread it out. It's just more or less, maybe if I would have done 2 more passes, it would have held together better. But again, we're just looking at single passes here. And yeah, so I wouldn't anticipate anything more than what happened here. Penetration, the whole original edge of the plate still there. It had 0 penetration on this. And had I ran any more amperage, it just would have had even worse arc blow. So realistically, 312 is not something you should be welding mild steel together, especially thick plate, unless it's all you have. Now, keep in mind, guys, 312 stainless is an awesome tool for your toolkit, because if you were to run into high carbon steel or castings or any number of things, anvils, leaf springs, you can weld them successfully with 312 stainless. Now, I'm not saying that you should go and put 10,000 pounds in the bed of your pickup truck after running a pass on the leaf spring in the back with this crap, but you would be able to get out of the mountains of Afghanistan with this. So to put it in perspective, so in an emergency, awesome life-saving tool, but you don't want to make a habit of using this to build stuff, especially over 7018. Now let's look at the hard face. So the hard face is probably the most interesting bend or break result that I've ever seen testing. And it made a okay looking weld. I knew it was going to perform bad. I thought it was going to be hard as a coffin nail, and once it hit about 5,000 psi, it was going to jet out of that press into a low Earth orbit, but that is not what happened. Literally, I put a couple 100 pounds of pressure on this and it failed. So that was hugely unexpected and pretty wild if you ask me. Now this rod did actually have some penetration. It did break down almost the complete edge of the plate. Very thin throat depth of the weld. Had I done multiple passes, it wouldn't have been any better, I can tell you that. So very brittle. But again, this particular rod is really meant to do a single pass on something, and it's not designed to be layered, and it's just meant to be hard and wear really well like iron. So it excels at that, but it definitely does not excel at joining 2 pieces of metal together. But it would no doubt worst brake test I've ever seen on this channel, so don't use it. Now the 11018, this is kind of interesting. So the plate itself tore. I've seen this before, but the way that it tore is a little bit different. And I would have to take a guess, and an educated one at that, and say what's going on here is the angle that these plates are at when I put all that pressure on it, and the lack of any kind of stretch on this weld basically put all of the force right on the toe, and it just ripped the plate through. So I saw that with 6011 before, and not nearly at the pressure that this was at. So I think it's, like I said, just that the weld doesn't give. Now, does this mean it's stronger than 7018? I would say no doubt this weld is higher tensile strength weld than 7018. The problem is that if you're using this rod to glue together mild steel, do you want stuff to just tear like this if it gets an impact force or a high stress, or would you like the weld to be a little bit ductile, give a little bit, and allow things to move and not just completely fail? And that's, I guess, the key point about this, is that 7018, to me, is a really good blend of ductility and strength, to where stuff tends to bend and hold together and likely handle vibration better in the long run. Now this, my guess is if I were to weld something that experienced high vibration, it would probably break just like this over time. So not something you want to, again, make a habit of using on stuff. Now, there is also another possibility, and that is that there was a crack that already existed here during cooling, due to the fact that this material is pretty sensitive to that. So is the base material. It's designed to be welding. I don't know, and I won't be able to test for that. All right, well, let's go to conclusion. So I brought out a couple 7018 and MIG welds here just to kind of give an example. All of these have no real issue passing a pretty significant bend on this test. Now this test is not a perfect AWS spec test. That's something I caught a lot of heat in the past on about this, and I'm not intending to make this an exact scientific test. I'm trying to make it relevant and accurate to what the average person might weld. And for most of what we're welding in the home or what you're repairing, 7018 and ER70 MIG wire is about the perfect blend of strength and ductility to make something that can take an impact and not just fall apart. When you start getting into these, no doubt they're stronger in tensile strength, or at least some of them, these 80,000 blue rods, who knows what their spec is, but that doesn't mean it's better. And one of the things you guys got to remember is that what you're welding probably doesn't see just a static load. If it sees just a static load, like you're hanging something on it forever and it doesn't experience vibration, these very well might be able to handle more of a load, stressing that weld downward. If it's, say, a pipe hanger or something, it might. But with the second you start adding vibrations or a dynamic load to it, having a stronger, more brittle weld isn't necessarily a better thing. And that's why when you get into stuff like your 7018 and your ER70, it tends to perform really good across the board. No, it's not the strongest, highest tensile strength weld. However, it will handle vibration likely better than a lot of these. And in all fairness, most of these are really specific rods for specific material, and you wouldn't be using them because you're not welding high strength steel. So that's all things to consider. Now, had I done this test with 3/8 high strength steel, then I have a feeling that we would start seeing the issue of ductility and lack of strength on these being an issue, because the weld would fail long before the material ever would, and we would be able to maximize the stress on that weld. And the difference in that case of how much weight something could hold using the right rod would be huge. Not to mention, depending on what you're welding, like if you were welding high carbon steel as a repair, 312 stainless would last far longer than any ER70 or 7018 material. And that's because it doesn't become brittle with the carbon absorption. All things to consider, I guess. So I guess the key takeaway is, if you want to make strong welds and do some repair, it helps to know what you're welding on. And if you're welding on high strength steel, you may want to be looking at 8018 or something stronger than that. And that's where contacting the manufacturer of what you're working on is to find out what it is it's made out of will actually make a difference. If you underweld that, it's entirely possible the weld will fail. Not to mention, if you weld on high carbon steel with a 70 series filler, it's going to become very brittle and it's going to perform more like this blue rod 80 series, or in a worst case, it might even perform like hard face. And I've seen it before when guys weld trusses on rear axle housings and they do it with MIG, and you hit a rock and it busts straight off the casting, just like this did. So it's all things to consider, and it really comes down to at least having an idea of what you're welding on. So with that said, hopefully you learned something today. And if you got any comments, questions, you know where to leave them. Until next time.